Hi everyone, my name is Priya and my net ID is PMR21004, and today I'm going to walk you guys through Pollard Row's algorithm for prime factorization. So let's get started. Pollard Row's algorithm for prime factorization takes in a positive integer n that is composite and finds its divisor. Say n equals to 187. Then the algorithm would output 11 or 17. Now I'm going to walk you guys through how this algorithm works. First, you want to define a polynomial g of x is equal to x squared plus 1 mod n. Now you're going to let a variable x naught equal to 2, and 2 is just some arbitrary value. Now you want to generate a sequence xi that is equal to g of xi minus 1. This means that the sequence xi is equal to g of 2, and so on. And this can overall be simplified down to xi is equal to g applied I times 2 x naught. Now this can be visualized as a series of dots, and that can be shown here. Now, because there's a finite number of answers, because n is a unique value, and we're modding by n, so every previous term will depend on it, you will eventually get a number that has already appeared in the sequence, and that will create something that looks like this. You can note here that this cycle looks like the Greek symbol rho. For step 3, we want to define two variables, the turtle and the hare, and place them both at x naught. The turtle will be equal to g of t, and the hare will be equal to g of th. Take both the turtle and the hare and start them off at x naught. Now on the iteration, the turtle will move to x1, and the hare would move up to x2. And now the next iteration, the turtle will move to x2, x4, and so on and so forth. For step 4, we want to implement a check at every iteration, and this would be the GCD of t minus h and n, and checking if it is greater to 1. Now we have three possibilities. One is if t equals h, and that would mean we are passing in the GCD of 0 and n, and that would give us n, which is greater to 1. Our second possibility is if we get a number d. D from our pass would be a factor of n, but it would not be equal to n or 1. Therefore, we found our factor and we can stop. Our last option is if d equals 1, and this would mean that we have to keep going. Now let's go over why this algorithm works. At the end of our algorithm, we will obtain a number d that divides n. And here we have two options. If the number d equals n, then we learn nothing. We have to go back to our original equation, and we have to change our original polynomial to change this value here to something else, or we have to change our value of x naught, or our second option would be if d is not equal to n, and now we have a value that is actually useful. Say we take the same sequence xi and now mod it by d. This means that our original cycle has only d possibilities to take on, and so the max length of the cycle here would be less than or equal to d. Now let's look at the stop condition. The greatest common divisor of t minus h, and this is equal to d. So what this really proves is if t is congruent to h, because this would mean that t minus h is a multiple of d. And what this would mean, or prove, is that the turtle and the hare are at the same place on the new sequence. Look at the sequence and take it as pseudo-random numbers with n unique values. Before the sequence repeats itself, there are O of the square root of n terms. This means that our new sequence will cycle till O of root d before it starts repeating itself, and our first sequence will cycle of O of root n. Now keep in mind, d is less than n. Therefore, on average, the turtle and the hare will end up at the same place on the new sequence, so you will hit the second, not the first choice of the stop condition. Therefore, you found a non-trivial factor of n. In general, we are comparing this method to the brute force method, which would have the runtime of O of square root of n. Now, keep in mind for this algorithm, we are basically looking at the collision for the second cycle here. So we would not be looking at the square root of n, but we would actually be looking at the square root of d. Now you can note that the largest value d can take on is the square root of n. So you can simplify this down to O of n to the 1/4 time.
This is the implementation of my algorithm. When I pass in 187 and I run my code, it returns 11 or 17, as mentioned previously in this video, and it also returns the time it takes.
Thanks for watching, and here's my works cited.